Chemistry chapter has to do with electrochemical cells and free energy. Remember Gibbs free energy from chapter 19. Cell potentials. Delta G, which is the free energy, remember, is equal to minus NFE, or that's for non-standard. Standard, it's minus NFE standard. Okay? Now, N is the number of electrons that are transferred within the reaction, and F is Faraday's constant. 1 mole electrons is 96,485 coulombs. Okay, this will be given to you, the constant, before you take this part of the test. Okay, so if we are to combine free energy, this is non-standard and this is standard. So we can relate the non-standard energy to the standard energy. And if you're dealing with non-standard, then that means that you are at some point in the reaction, and so you're equal. It's a Q problem. So this tells you that you're either to the left, to the right of the reaction. R and T are constants. R is going to be the gas constant again, and temperature in Kelvin. Okay, more about those as we get to them. Okay, we said Faraday's constant. Michael Faraday is the one who did a lot of work in electrochemistry, and hence he got the constant. Okay, so here we go with our cell potentials. We're going to run through some equations, and I'm going to tell you which ones you're responsible for. You're responsible for these two, pretty much the same equation, standard and non-standard. And then we're going to get to these two. All right, now this one is the simpler, and this is the form you're going to use, but it comes in two varieties. So as we look at it, if you'll notice that we have the non-standard cell. Here's our standard cell. And then this is all related to a Q problem and converting back and forth. Okay. And we will continue on. And if it's non-standard, the amount of work done on a cell can vary. This is like when you take a battery. If you buy it brand new, it says to have a certain charge on it. As you use it, the charge rolls down. And sometimes you can use an older battery that doesn't have as much charge for something that doesn't need the full charge, etc. So if you're dealing with some sort of cell that is not at full charge, or it could be greater charge actually even, then you're dealing with the Nernst equation. Now, closer look could be electrical work, but here's the Nernst equations. So you're going to start with this variation of this equation we said that we would be dealing with. And the two forms that we're going to use are these two right here. Now, these give you pretty much the same answer. What's the difference? Well, if you look at it, we have negative RT NF natural log of Q right here. So if you take these constants and use the natural log, then you combine them to get this value here. If you use the base 10 log, you get a different constant. Notice that N doesn't change. It's the number of electrons transferred. And that is the total number of electrons transferred. So when we were balancing equations, so that was the number of electrons that canceled when we were balancing. So that's really the only difference. Both forms are going to be on the equation sheet. Which one you pick is a function of whether you prefer the natural log or the log. You're going to pretty much get the same answer. Okay, so again, same part up here, but if you look down here, then we have if Q is equal to K, then you're at equilibrium, and E cell non-standard is 0. So if that's the case, your E cell standard is equal to this value for the natural log of K and this one for the log, base 10 log. Now the difference is if you're trying to get rid of the log, then remember the inverse of natural log is e to the x. The inverse of base 10 is 10 to the x. And remember, what the Nernst equation really is the non-standard cell. Okay? And we actually worked this before. So when we did this one in chapter 19, remember we got to this equation where we had the free energy divided by the gas constant. Well, in this case, the free energy is basically replaced with the number of electrons that's in E cell. It's the standard potential, and this is all the other constants work together. So what this will allow you to do is determine the equilibrium constant based upon the cell potential. Okay, so this is actually a good slide to look at because this relates delta G to E cell to K. And this shows you the relationship between free energy and E cell. And then this relates you to K. And this one relates K to free energy. Okay, so basically all of these are equations you may need to use at some point in time. So let's work on trying to work on these equations. But before we do that, the first thing we need to do is we need to be able to calculate the moles of electrons transferred. This is sometimes really easy and sometimes really difficult. If you'll notice, we have a variety of equations here. They're already balanced. When you have one of these on the test, I will give you a pre-balanced equation. I'm not going to give you an unbalanced equation on the grounds that if everybody balances it wrong and differently, then it's much harder for me to grade. So the beauty of this little trick is you can pick either the oxidized species or the reduced species. It really doesn't matter in any particular equation. So when I look at equation A, the first thing I notice is I got an elemental there. So when I come over here, I'm 4 plus. Okay. No, I'm not. I'm 2 plus. I can't do math. Okay, I'm 2 plus because it's CO, not CO2. That being the case, what for each carbon, I am transferring 0 to 2 plus. So I am losing 2 electrons per carbon, and I have 10 carbons, so I am transferring 20 electrons total. Now, as a double check, you can look at the other species, which happens to be phosphorus, which is 0 here, and it happens to be 5 plus over here. If you take it apart and do the PO4 3 minus, it's easy to figure out. So again, phosphorus is going from 5 plus to 0, which means you're transferring 5 electrons times 4 phosphoruses, that's 20 electrons. So the oxidized species should equal the reduced species. Do you have to do both? Nope, but it's a nice double check. And so for the next ones, just for simplicity's sake, I'm going to do both of them just to show you, but remember you don't have to do that. So iron here is going from 3 plus to 2 plus. So it's transferring 1 electron per iron. And you have 5 irons, so it's transferring 5 electrons. The other option is the manganese, which is going from 2 plus to 7 plus. so it's transferring 5 electrons, and there's only 1 manganese. Okay, so copper here is going from 0 to 2 plus, so it's transferring 2 electrons, and times there are 3 coppers, so that's 6 plus. Nitrogen is going from 6 plus 5 plus to 2 plus, so it's transferring 3 electrons, and there are 2 nitrogen, so it's transferring 6 electrons. And remember, what's oxidized and reduced should balance. Iron again is going from 2 plus to 3 plus, so there's 1 electron per group, and there are 6, so that's 6 electrons. The other one is chromium, which is going from 14, 12, 6 plus to 3 plus, so it's transferring 3 electrons, times 2 is 6 electrons. Okay, now this last one is kind of goofy. Manganese is 7 plus going to 2 plus, so that's 5 electrons times 2, so we're transferring 10 electrons. So carbon over here is, this one is going to 4 plus, and over here it's 8, 6, so it's 3 plus to 4 plus, so it's transferring 1 electron times 10 carbon atoms, so there are 10 electrons transferred. Again, that one was a little tricky on the carbon, so you could have stopped with the manganese and moved on. Okay, so what do we do with this? Well, then we get to our first reaction where we're dealing with this. We're given a balanced redox reaction, use the standard reduction potentials, calculate E cell and delta G. All right, so first things first, zinc is gaining electrons, so it's E red, and we get negative 0.763 volts for our zinc. The other one is hydrogen. Hydrogen is E-ox because we're going from 0 to 1 plus. So it's 0 volts. So E cell is equal to E-ox plus E red, which is equal to negative 0.763 plus 0, so it's negative 0.763 volts for E cell. So this is a non-spontaneous cell, okay? So then what is delta G? Delta G standard is minus NFE cell. So we have to figure out how many moles of electrons are transferred. So going from 2 plus to 0, so that's 2 electrons times 1. So we're transferring 2 electrons. So we have minus 2 times Faraday's constant, which is 96.48485 coulombs. These are moles of electrons per mole of electrons. And then your E cell is negative 0.763 volts. So your moles cancel, then you've got coulombs, and volts are joules per coulomb. So we end up with a positive, because we have a negative on a negative, 147236.11 joules. If you want to make it smaller, you could say 147.2361 kilojoules. And so this is non-spontaneous because both E cell is negative and delta G is positive. So if it's non-spontaneous, it's going to favor the reactants. Remember, if it's spontaneous, it favors the products. So this allowed us to work two different problems within the same. So let's look for the next one for the reaction of nickel and zinc. Find the cell potential if nickel is 5 molar and zinc 2 plus is 0.05 molar. Well, that's a non-standard cell. And we know it's non-standard, standard, because molarity is not equal to 1. Okay? So E cell, non-standard, is equal to E cell standard minus 0.0592 divided by N times the log of Q. Okay? So let's see what we've got, and if we look at it, nickel's going from 2 plus to nickel 0, so it's gaining electrons, so that's E red. And if we look it up on the chart, E red is 0.7, whoops, no it's not. The nickel is negative 0.257. The zinc we just did before, except we're doing it in reverse. This is EOX, which is positive 0.763. So E cell is equal to EOX plus E red, which means it's 0.763 plus negative 0.257, all those volts. So E cell is equal to 0.506 volts. Okay, so I've got E cell. Now I've got to figure out N. So if you're looking at N, it's 2 moles of electrons. And then remember, then we have Q. Remember, Q is equal to products, which in this case is zinc 2 plus, over reactants, which is nickel 2 plus. And remember, the solids all go to 1, so they drop out. We don't have anything squared or cubed, so our Q then becomes, the zinc is 0.05 molar over 5.0 molar. So this is equal to 0.01. So if I go back over here and I plug in what I know, E cell is equal to 0.506 minus 0.0592 divided by 2 log of 0.01. Now, we could have used the natural log equation. It truly does not matter which one you use. So we get 0.506 volts minus 0.0296 times negative 2. So it's 0.506 volt minus a negative 0.0592. So E cell non-standard is 0.5652 volts for the non-standard cell. And this actually makes sense because you're like, it's bigger than the standard. Yes, if you noticed, it is positive, so it's product favored, and you have more reactants than you do products, so it's pushing it to the product side, so it is positive. Okay, here's a variation on a theme, and for some bizarre reason, don't know why, all of these have 2 electrons. Don't assume it's going to have 2 electrons. This one wants you to calculate the equilibrium constant. Okay, now there are a couple ways to do this, but if we start with E cell standard is equal to 0.0592 N times the log of K, then the log of K is going to be equal to E cell times N divided by 0.0592. The inverse of log is 10. So K is equal to 10 to the E cell. standard times N divided by 0.0592. Now, this is different than the other version, which is K is equal to E to the E cell standard times N divided by 0.0257. So what's really different is the constants are different. It doesn't matter which one you use. So let's go back and look at it. In both of them, we need E cell and we need N. So N, if we look at it, is 2 moles of electrons. So if you look at it, iron is EOX, which is equal to positive 0.440 volts. Copper is E-red, which is equal to positive 0.340. So E cell is 0.780. So that gives us our E cell value. So it doesn't matter which one you come up with. But K, we're going to do the first one here, is 0.780 times 2 divided by 10 raised to the 0.0592. That means it is 10 to the 26.35135, which means that K is equal to 2.2457 times 10 to the 26th. If you were to work it out using the E function, you would get 2.3006 times 10 to the 26th. Notice that you pretty much have comparable numbers. They vary slightly, but you're going to get equal values. And I highly recommend that on this one, you make sure that you work the numbers so that you can get the numbers that I got, because this starts to get tricky in your calculator. Okay, now, side note here, this is how pH meters work. pH meters work based upon an electric current, based upon the number or the concentration of the hydronium ions. So I just thought I'd show you this. You're not responsible for it other than knowing that that's how pH meters work. This is one of the little lanyard information things in your text, and it has to do with electric eels, and this is just kind of cool. And electric eels are cool. Okay, heartbeats and electrocardiography. A number of y'all are associated with medicine, etc. This may be a cool way to understand how to read this. Okay, the next section is batteries and fuel cells. I want you to classify the batteries as primary, secondary, or fuel cells, what the kinds are defined as, whether you'll hear people refer to, oh, that's an alkaline battery, a lithium battery, NiCads, etc. So what I want you to do is basically take each of the batteries and classify them, and then I will put up a submission assignment so that you can upload this for extra points on this exam. Okay. So a couple of y'all have asked about extra points because y'all are finding this very fun. That was sarcasm. So here's one that you can use for bonus points. It will go up probably on Monday. You just got to remember to upload it because it will close. And last but certainly not least, this is the batteries for the hybrid and electric vehicles. And the batteries are being changed because, people just don't like their garages to go up in flames on them. So this talks about the batteries and the problems with the batteries and the densities, etc. So this is really interesting to read through and look and see what the issues with the different batteries are.